So 4-4 is concavity in the second derivative test. You've already seen that locating the intervals in which a function f increases or decreases helps to describe its graph. In this section, you will see how locating the intervals in which f prime increases or decreases can be used to determine where the graph of f is curving upward or downward. So definition of concavity, let f be differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing. So let f be differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing on the interval and concave down. So concave downward on I when f prime is decreasing on the interval. The following graphical interpretation of concavity is useful. Let f be differentiable on an open interval I. If the graph of f is concave upward, so this one is concave up, then the graph of f lies above all of its tangent lines. And then this graph is really light and you can't see it, but if you look at these little points on here, there's these little light colored tangent lines on there. It looks better in your book, but that's just where it's showing you all these tangent lines lie outside or underneath that curve. And it's the same thing for the concave downward. They're just all above them. So let f be differential on an open interval. If the graph of f is concave downward, then the graph of f lies below all of its tangent lines. So same thing, every little point has like a lightly drawn tangent line, and you can see that the curve is below all of those. Any questions? Everybody okay? All right, moving up. To find the open intervals on which the graph of a function f is concave upward or concave downward, you need to find the intervals on which f prime is increasing or decreasing. Okay. For instance, if we have f of x equals 1/3 x cubed minus x, and I'm going to graph this one for you. You don't have to graph it. I'm going to do it for you. Looks like this is concave downward. On the open interval, so basically you look for your maximum and then you tell me what part makes up that specific maximum or parabola. So it is concave down until it gets to 0, and that's your turning point where it becomes increasing again, or it starts to be that other minimum. So on the open interval, negative infinity to 0. Because f prime of x equals x squared minus 1, the derivative of 1/3 x cubed minus x is x squared minus 1. So 1/3 times 3 is 1. Drop it to the power. 1 less power is x squared. And then the derivative of negative x is negative 1. We're going to look at that one as well. It's also decreasing there. Does everybody see from negative infinity to 0, it's decreasing. And then from 0 to infinity, it's going to be increasing, that red line. Does everybody understand that? All right. Similarly, the graph of f is concave upward on 0 to infinity. And that's because the derivative is increasing on 0 to infinity. So it's much easier to look at the derivative and know where it's decreasing versus increasing, rather than trying to figure out that turning point and looking really hard at it. Everybody understand? So that's all I'm saying. You can see it from this graph, but it makes it easier to see it from this graph. Okay. The next theorem shows how to use the second derivative of a function f to determine intervals on which the graph of f is concave upward or concave downward. Let f be a function whose second derivative exists on an open interval I. If f double prime of x, or the second derivative, is greater than 0 for all x in the interval I, then the graph of f is concave upward on that I, or in that interval. If your second derivative is less than 0 for all the x and I, then f is concave downward on I. To apply theorem 0.7, locate the x values at which f double prime of x is equal to 0, or where f double prime does not exist. So what would that part be, the do not exist part? So asymptotes. Okay, so that's what it's asking. So remember, sometimes we set our derivatives and we got our critical numbers, but then we had to go back and do our denominators equal to 0 as well. So that's what it's saying. Make sure you get your critical numbers and then get your vertical asymptotes and anything else. Use these x values to determine test intervals. And then finally test the sign of f double prime x in each of the test intervals. Same thing you did yesterday. Just today we're doing it with the second derivative. Got it? So it's the same exact thing you did yesterday. All right. Determining concavity, determine the open intervals on which the graph of f of x equals to e to the negative x squared over 2 is concave up or concave down. So we need to find the second derivative. So we're going to start with the first derivative. So to find the first derivative, remember e to the negative x squared over 2 is going to be your first part, and then you're going to take the derivative of the power. So it looks exactly the same, and then times the derivative of the power. So rewrite it. And then up here, I'm going to rewrite this so you can see it a little bit easier. That power is negative 1/2 x squared. That makes it look a little bit simpler to take that derivative. All right, so what's the derivative of negative 1/2 x squared? Just negative x. So then your first derivative is negative x e to the negative x squared over 2. What do I have to do for my second derivative? Product rule. Product rule. So the derivative of the first one, derivative of negative x is, rewrite the second one, plus, write the first one, and then we've already taken this derivative. What is the derivative of e to the negative x squared over 2? Keep going. Remember, it's all of it together, right? What do you notice that they both have? They don't both have a negative x. Mhm. When I factor that, I get a negative 1 minus x times negative x is plus x squared. But remember, they hardly ever write it like that. I'm happy with it like that. That's fine. But they'll turn it around. So when you guys look in your book, they have turned it around. So this is your second derivative. Do exactly what we did yesterday. You're going to set the second derivative equal to 0. You're going to set each part equal to 0. How do I solve the first one? Can I ln 0? No, so this one doesn't work. Yes, sorry. And then how do I solve that? Take the square root, and what do I get? Plus or minus 1. There are no denominators, so I don't have any other numbers that I have to worry about where it doesn't exist. So now I have my intervals. Did it specify an interval? So what do we use? So we're going negative infinity, less than x, less than negative 1, negative 1, less than x, less than 1, 1 less than x, less than infinity. Yesterday I got tired of writing these intervals, so I did just like I told you, do the dash or whatever. That is fine. Y'all don't stress out about having to write it specifically like this. What do we do now? Yep. So what's a test value between negative infinity and negative 1? Between negative 1 and 1? And then bigger than 1. Remember, we're plugging it into what? Which one? Second derivative. So I put it into my calculator. I'll move my calculator in a minute so you guys can. Tell me if I screw it up and put it in wrong. This calculator's like sticking bad. And then I've changed all my stuff, so I'm going to go back to my table set and make it ask. So I'm only looking at the ones that I want. -2, 0, and 2. What do you notice about -2? It's greater than 0, so it's increasing. 0 is less than 0, so it's decreasing. Greater than 0, so it's increasing. That's all you have to do. Now, in your homework last night, it told you to find the relative max or the relative min. So I'm going to talk to you about that real fast. It has nothing to do with this, but I'm going to use this as an example. So we set our first derivative equal to 0. We got our values. Whatever your critical numbers are, that's where your extrema are going to be. So to find your y coordinate, you plug it into the original equation. So our critical number was -1. We would plug it back into the original equation to get our y value. So if they ask me for a specific point, it is your critical value for x plugged into your original equation. Okay, and we'll go back and do that eventually. I just wanted you to focus on the chart. Got it? So you know that it's where it changes from increasing to decreasing or decreasing to increasing. All right. Note that the function in example 1 is similar to the normal probability distribution function. And you probably don't have any clue what that is. Have y'all ever heard of that? Whose general form is f of x equals 1 over sigma square root 2 pi e to the negative x squared over 2, and then sigma squared. Sigma is the standard deviation. Sorry, I'm gonna just write it smaller so it'll fit online. And that little symbol is the lowercase Greek letter sigma. This bell-shaped curve is concave downward on the interval negative sigma to sigma. The function given in example 1 is continuous on the entire real number line. When there are x values at which the function is not continuous, these values should be used along with the points at which f double prime x is equal to 0 or does not exist to form the test intervals. So again, when it's not continuous, points of discontinuity, you want to make sure that those are used as well. Everybody good? Determining the open intervals on which the graph of x squared plus 1 over x squared minus 4 is concave up or concave down. So again, those intervals, same exact thing. What do we have to do? Find the second derivative. So for that, we got to find, which really sucks because we have to use quotient rule. Okay. So the derivative of the top is times the bottom minus the derivative of the bottom times the top all over the bottom squared. Clean up the top. I have 2x cubed minus 8x, so I distribute my 2x. 2x cubed minus 8x. 2x times x squared, and a minus is 2x cubed again. 2x times 1 is 2x, and it's minus all over x squared minus 4 squared. Your 2x cubes will cancel out You're left with negative 10x over x squared minus 4 squared. So there's your first derivative. Second derivative, quotient rule again. What's your derivative at the top? No. The top of the, yeah. Negative 10 times x squared minus 4 squared minus derivative of the bottom. What is it? 2 times to the 1, so we don't have to write that, times 2x, and then don't forget the top. All over x squared minus 4 squared. Oh, sorry, to the 4th. Thank you. All right, what do I do now? So on the top, I'm going to leave this negative 10 outside of this x squared minus 4 squared because I'm too lazy to do that part right there, which is fine. It's fine. Over here, though, I'm going to go ahead and multiply my stuff together. What's negative 10 times 2 times 2? And then I have a minus, so it's going to be, and that's x squared because it's 10x times 2x. And then we still have that x squared minus 4 in there. What do you see on the top? Did I say that they have an x squared minus 4 in common? All right, so I'm going to go back over here. Take out my x squared minus 4. Everybody okay? That leaves me with negative 10 x squared minus 4 plus 40x squared over x squared minus 4 to the 4th. Your x squared minus 4, one of them will cancel out, and that'll change to cube on the bottom. And then just clean up the top. You have negative 10x squared plus 40 plus 40x squared over x squared minus 4 cubed. This gives you 30x squared plus 40 over x squared minus 4 cubed. This is fine, but they go ahead and take the 10 out as well. So the actual final, sorry, 3x squared. Second derivative is 10 times 3x squared plus 4 over x squared minus 4 cubed. Once we get that derivative, the reason that they go ahead and do everything is because once we get that derivative and set it equal to 0, remember you multiply your denominator over. And we still get 0. We'll divide by 10. Still get 0. And then what happens? Subtract the 4, divide by 3. What's wrong with this? No values for x here. What's the other thing I need to check? The denominator. So what was our denominator? We're going to cube root both sides, still going to give us 0. We're going to add our 4, square root, and we get positive and negative 2. Make sure that they didn't give you an interval that you don't need to use one of these for. They do not. So you're good to go. That's going to make your test intervals. So what are your test intervals? Negative infinity, less than x, less than. What's your littlest x? Negative 2. Then we're going to go negative 2 to 2. And then 2 to infinity. What value can I pick for the first one? Negative 3. The next one? And the last one? 3. We're going to put our second derivative in. 10 times 3x squared plus 4 over x squared minus 4 to the third. We're going to ask about negative 3, 0, and 3. Again, it doesn't matter what the numbers are, just whether it's positive or negative. The first one is greater than 0. The second one is less than 0, greater than 0. Can there be greater than 0, and then a less than 0? Yes. Okay, so don't assume that it's going to alternate every time. So this would be concave up, concave down, concave up. So again, we're not doing anything different. We just got to do more steps by taking the second derivative. Same exact thing just right. Right? The graph from example 1, and that's found on page 228, if you want to look at that, has 2 points at which the concavity changes. If the tangent line to the graph exists at such a point, then that point is a point of inflection. You've learned about points of inflection for a long time. It's the exact point where a graph changes from increasing to decreasing. Does everybody understand? Increasing to decreasing. 3 types of points of inflection are shown below. And quite possibly there's only 2 of them. I don't know where the third one is. But the third one is going to look like your cube. So like x cubed is going to go right here. The definition of a point of inflection: let f be a function that is continuous on an open interval. And let C be a point in the interval. If the graph of f has a tangent line at C, f of C, then this point is a point of inflection. Of the graph of f, when the concavity of f changes from upward to downward, or downward to upward. At the point. The last couple of examples, these last two pages are really easy, just to throw it out there. So you just did the hardest one. Okay. The definition of point of inflection requires that the tangent line exists at the point of inflection. Some texts do not require this. For instance, using this definition, the function. This is going to be a piecewise function. X to the third when x is less than 0. X squared plus 2x when x is greater than or equal to 0. Does not have a point of inflection at the origin. Even though that should say concavity. I thought I got all of them. Of the graph changes from concave downward to concave upward. Do y'all know how to put piecewise into your calculator? Have y'all ever done it?
It's been a long time since I did.
I never did it till this year. I didn't know how to do it. So I'm gonna show y'all how to do it. So if you have one.
I could have swore you showed me. You showed us. You showed us, I've been showed before.
Unless I've showed you this year, I've never showed you.
You did show us, but we all forgot.
That's okay. I'm gonna show you how to do it. Just in case you have one in your homework. I don't remember if it's you guys or pre-cal that has it in here. I can never remember. Because y'all do the
I
same
think we
thing.
showed us yesterday.
Did you have one yesterday? I knew there was one somewhere. All right. So it's not super important that you know how to graph it. That just helps you with your continuity and stuff like that. But just so you know how to graph it, when you go into y equals, you're going to do your alpha y equals. And in the top, you're going to put your function, which is x to the third. But in the bottom, you're going to do this x less than 0. So put in your x, and you go to math, not math, second math. And we have less than 0. And that'll make the first one. Like it's legit that easy. So go to your second one, alpha y equals. On the top, you're putting in your function. On the bottom, we have x, second math, greater than or equal to 0. And then when you graph it, it'll show both of them. And you can't really see it up here, but one half of it is blue and one half is red. So you'll know which one is which. Does that make sense? Everybody see that? So then you can see that our point of inflection is at 0 because it goes from that it has that little hump right there and then goes back up. To locate possible points of inflection, you can determine the values of x for which f double prime of x is equal to 0. Or f double prime x does not exist. It's the same thing that we've just talked about. I'm sorry, y'all. This is similar to the procedure for, oh my gracious, locating relative extrema of f prime. And I've been saying that the whole time. We're not doing anything different today except for taking that second derivative. Stressing me out. Theorem 4.8, points of inflection. If C, f of C is a point of inflection on the graph of f, then either f double prime of C is equal to 0, or f double prime does not exist at x equals C. All right. Determine the points of inflections and discuss the concavity of the graph of the f of x equals x to the fourth minus 4x cubed. So what do I have to do? Find the first derivative. What is the first derivative chart? Tell us. What are we looking for that? But for what? What does it tell us? Points. What are those points called? Not inflection. We're doing inflection today. What are those points that we worked on yesterday? Max or mins? Oh, first derivative charts tell you where relative max and mins. It's okay. It's okay. Relative max and mins. That's why we're going over it. That's why we're going over it. So first derivative tells you where your relative max and mins are. Okay. Yes, you do increasing and decreasing, but where they change is where either your minimum or your maximum is. F double prime, or your second derivative, tells you points of inflection and concavity. Does everybody understand that? Okay. So find the first derivative. What is your first derivative? So that one was really easy, right? F double prime is perfect. To find our concavity and the points of inflection, what do I need to do? 0. How do I solve this? The 12x gives you that x is 0. X minus 2 gives you that x is 2. We don't have any denominators, so we don't have any points where it doesn't exist. Does it give you an interval to look at? Nope. So what is our intervals? Less than x, less than. Your littlest one is 0. 0, less than x, less than. Your next one is 2. And then 2 less than x, less than infinity. All right. Give me a value. -1, 1, and 3. Plugging that into the second derivative. 12x squared minus 24x. What? No, I did not do that. And we're plugging in -1, 1, and 3. So we get greater than 0, less than 0, greater than 0. That means greater than 0 is concave up, less than is, and again, greater than concave up. Where are your points of inflection? This is what I was talking about earlier. The one thing that I told you or didn't tell you to finish off was making those points. Let me show you this graph. Hold on. This is the graph of the original function. A point of inflection is where it turns. So it goes from increasing, decreasing, decreasing, increasing, whatever. So if we look at this graph has a turning point right here. Where's this point? 0, 0. Here's how you get it. Right here, we change from up to down. Does everybody see that? Anytime it changes, you're going to have a point of inflection. It's at 0. That was my critical number, or my number in this case, where f prime or double prime was set equal to 0. How do I get the y coordinate? You plug it back into the function. What's 0 to the fourth minus 4 times 0 to the third? That's 1 point of inflection. That's the one thing that I didn't show you yesterday. Okay. And again, it was so that you could get that chart and we could talk about it today. So then you have a 2 for your x. Why am I using the 2? Because it went from down to up. So I know that that's a point of inflection. And then just like before, I'm too lazy, so I'm gonna put 2 into my calculator and I get -16. Again, you can just plug it into the formula, but I already had it into y equals, so I just stuck it in my table. Any questions? So your points of inflection are 0, 0, and 2, -16. The converse of theorem 4.8 is not generally true. That is, it is possible for the second derivative to be at 0 at a point that is not a point of inflection. For instance, the graph of f of x equals, I don't know if this is x to the 4th or x squared, doesn't matter. Let's see. 2x. Nope, let's just do x. If it's different, I'll get it in a minute. Where the second derivative is 0, it is, it's gonna be x squared. When x equals 0. But the point 0, 0 is not a point of inflection because the graph of f is concave upward. In both intervals, -infinity less than x less than 0, and 0 less than x less than infinity. I don't think that's right. Let me look it up. I can't tell if I wrote a 4 or a 2. That's what happens when I'm trying to get it done. It's a 4, sorry. The second derivative test, in addition to testing for concavity, the second derivative can be used to perform a simple test for the relative maxima and minima. Maxima and minima. The test is based on the fact that if the graph of the function f is concave upward on an open interval containing c, and f prime of c equals 0, then f of c must be a relative minimum of f. Similarly, if the graph of the function f is concave downward, on an open interval containing c, and f prime of c equals 0, then f of c must be a relative max of f. All right, so this paragraph just explains what this second derivative test tells you, but this makes it look a lot easier, okay? And then we'll do it and be done. Let f be a function such that f prime of c equals 0, and the second derivative of f exists on an open interval containing c. If f double prime of 0 is greater, or sorry, f double prime of c is greater than 0, then f has a relative minimum at c f of c. If the double prime is less than 0, then it has a relative max. At c f of c. But if it's actually equal to 0, then the test fails. That is, f may have a relative maximum a relative minimum, or neither. In such cases, you can use the first derivative test. All right, so this example is just using the second derivative test to figure out the relative extrema. So we already knew yesterday how to do it by the first derivative. It's just telling you to do the second derivative, so you don't have to do two different charts. That's all it is. Okay. So find the relative extrema of f of x equals negative 3x to the fifth plus 5x cubed. So we're going to use the second derivative test. So find the first derivative. What is it?
Negative 15x to the fourth plus 15x.
Find the second derivative. Negative 60x to the third plus 30x. And then you still have to find all of your critical numbers, all of your critical numbers. So on this one, we're going to factor out a negative 15x squared. You get x squared minus 1 equals 0. Your 15x squared causes a 0. For this one, you'll add 1 and take the square root. So you'll get positive and negative 1. For your f double prime, I can factor out a negative 30x. Gives me a 0. And what else? Yes, because I factored out a negative. Thank you. So a 0 and we can leave it as square root of 1/2 for right now. We're going to talk about this. So typically what we would need to do to be able to find our relative extrema is take our 0, 1, and negative 1, make our chart, and figure that out. So what you can do this time is instead of doing all of that, you're going to have a point, the sign of f double prime of x, and your concavity. We do not have to use any of these other, I just did this for fun, not for fun, just to keep you in the head game of that, okay? With the second derivative test, it says just check the points, check your critical points and see what your concavity is at each point. So if it's greater than 0, you're gonna have a minimum. If it's less than 0, you're gonna have a max. And then if it's equal to, it's gonna fail. So your points are based off of these values right here, okay? So these don't really matter in what we're doing right now. They would matter in the previous problems, okay? So your first point is going to be negative 1 something. Your second point is going to be 0 something. And your third point is going to be 1 something. How do you get that y value? To which one? The original one. So again, I'm kind of lazy, so I'm going to put it into y equals, because I can get it done all at the same time if I do this. So negative 3x to the fifth plus 5x to the third. And then my values that I'm plugging in are negative 1, 0, and 1. So my coordinate, when I plug in -1, I get -2. When I plug in 0, I get 0. And when I plug in 1, I get 2. So this was from plugging in f of -1, f of 0, and f of 1. That's where those came from. Right. Then I need to check the sign of f double prime of x. So f double prime, -30x, 2x squared minus 1. And I plugged in those values. What did I get for the first one? A positive. What did I get for the second one? I got 0. And what did I get for the third one? A negative or less than 0. So your conclusion, if it's greater than 0, it's a relative min. If it's equal to 0, it fails, so it's neither a relative min or relative max. And if it's less than, it's a relative max. I honestly do not care which way you do it. If you do the second derivative, if you do the second derivative or the first derivative and go from there. Any questions? All right, homework. Page 232. 5, 11, 17, 23, 25, 29, 31, 33, 39, 41, 51. Do y'all have any questions on last night's homework? Okay, don't yell them out just yet. Give me a minute. All right, so everybody got all of that? All right, remember I'm still recording. Guys, if you don't have anything for 4-3, you need to go ahead and start 4-4. If you have questions on 4-3, I need to know what those are. Anything else other than 45? 19, come on. Anything else? All right. 19. Add f of x equals x squared. ln x over 2. If I'm doing some of the problems in the very beginning, that means you probably didn't start your homework. You should ask questions when you're in class. Make sure you guys are watching this. So half the reason that you're gonna miss this is because you didn't look up your derivative for LN, and it's in the front of the book. Remember, you guys have those rules. Okay, so when we do this, your first derivative, you're gonna use the product rule. The derivative of x squared is 2x. And then you have ln x over 2 plus, you're gonna keep the first, the derivative of the other one, you do the rule in the front is u prime over u prime over u, which is 1/2 over x over 2. Remember that we don't divide fractions, we flip and multiply, which will actually just give us 1 over x. So I'm going to simplify it a little bit right here. We have a 2 on top, a 2 on the bottom. Can't do that. I don't know what I'm trying to do. Trying to do the other one. 2x ln x over 2. Here we have an x squared, and I said that this was going to be 1 over x. So I have 2 on the top, 1 on the bottom. That leaves just 1 on the top. So there's your first derivative. What do you notice about both of them? So our first critical value is going to be 0. I'm going to set 2 ln x over 2 plus 1 equal to 0. I need to get ln by itself. I'm going to subtract 1. Divide by 2. How do I get rid of ln? I'm going to e both sides. This is the same thing as 1 over the square root of e. To solve for x, I just need to multiply by 2. You don't have to cross multiply, just multiply by 2. And I get 2 over the square root of e. If you gave me a decimal there, that would have been fine as well, because you're gonna have to know that decimal. But this is what your book will give you. Okay, I'm okay with the decimal. So we go negative infinity. Your 0 does not count. Why would your 0 not count? What happens when I plug it back in? Can it, right here, even if I plug it into the very beginning, I can't find this coordinate because 0 over 2 is 0. Can I do ln of 0? No, so that one marks out. So we're just going to square root of e. Square root of e. Your values you can test are 1 and 2. Doesn't matter. Anything less than 1, anything greater than 2 is going to work. You get a less than 0 and a greater than 0, which means that this is decreasing and this is increasing. Here's what I was talking about yesterday. If they, or this today, if they ask you, this is decreasing to increasing, so that would be a minimum at 2 over square root of e, and whatever that gives you when you plug it back into f of x. Does everybody understand that? Okay, so that's the one thing that I didn't show you yesterday. So if you were looking in the back or you were looking at your answers and that had coordinates, that's where the coordinates were coming from. Okay, so there's 19. $37. We had f of x equals 2x. And then I think it did 1 over x. But I just went ahead and changed it to x to the -1 to make it easier for me. First derivative. Is 2 minus x to the -2. Which changes into 2 minus 1 over x squared. You set that derivative equal to 0, which means I'm going to add my 2 over. You could also just add to make it positive the 1 over x squared over. You can switch these. So when I solve it, I get x squared equals 1/2. And then I have to take the square root. And they don't like looking at it like this. So they multiply by the square root of the square root. And you get positive negative square root of 2 over 2. What's the other value I need to find? Those are my critical numbers. What else do I need to do? You have a denominator of x squared. Is that equal to 0? So that means I'll get an x of 0 as well. You will go negative infinity to negative square root of 2 over 2. Negative square root of 2 over 2 to 0. 0 to square root of 2 over 2. Square root of 2 over 2 to infinity. I plugged in -3, -1/2, 1/2, and +3. They alternated until they got to this one. So greater than, less than, and then it stayed less than and greater than. So increasing to decreasing causes a max at negative square root of 2 over 2, and then whatever it is when you're plugged in. This is continuous decreasing, so there's nothing there. There's no relative max or relative min. This is decreasing to increasing. So this will be a min at square root of 2 over 2 and whatever you get for y when you plug it in. What part are you having trouble with? Is it the derivative part or is it
Yes,
anything?
yeah.
Okay. That's all I need this.
But I get all of that.
So like if I do the next one and I don't do all the chart, y'all are gonna be okay?
I get back to the chart.
All right, so you said 41 and 45. I just felt like when I started doing the chart, everybody was doing something else. All right. 41. This is that piecewise. F of x equals, I knew y'all would have questions on this one. All right. So you're actually going to take the derivative of both of them and then use those values that you have. So they give you that x is less than or equal to 0 and x is greater than 0. What's your derivative of 4 minus x squared? And then what's your derivative of negative 2x? Negative 2. So y'all should be okay with that part right there. You're going to set your derivatives equal to 0. And you're going to get 0 for the first one, so that's your critical number. If I try to set the second derivative, I don't get anything, so the only critical number I have is 0. You already got it. All right. I have to do your chart on this one, I'm sorry. All right, give me a value between negative infinity and 0. -1. A value between 0 and infinity. Okay. We have -1 is less than or equal to 0. So I plug it in here. What's -2 times -1? Which is greater than 0. But you had to plug this one in here because it was less than, your x value was less than or equal to 0. Everybody got it? So then this value is 1, which is greater than 0. So I use this derivative, which is less than 0. So -2 is less than 0. So this one was increasing and decreasing. So increasing to decreasing would be a max at 0. And looks like 4. Because if x is 0, you would plug it in up here. So I good? 45. I think y'all make your e's a little too complicated. It is, your e's are the exact thing as chain rule. It's kind of the same. So to find the derivative, I need to use the product rule. So I'm going to start with the first one, 3 minus x. What's your derivative? Times e to the x minus 3. Plus the derivative of e to the x minus 3 is e to the x minus 3 times the derivative of the power, which is 1. So I don't need to do that. But don't forget your first one. Write it down again. What do you notice about both of them? So I'm going to factor that out. Leaves me with -1 plus 3 minus x. That gives me e to the x minus 3 times 2 minus x. You have 2 parts set equal to 0. The first one I would try to ln, but I can't ln 0, so it's no good to me. Add your x over on the other one and you'll get a +2. Do your test values, find it. Question. So very good. Any more questions on this? All right.